Alrighty, hello everyone, and welcome to recording of discussion number 2. We have 12 total, so we will finish that second one today, leaving 10 more left over. So as I'm getting my screen share going, I just wanted to make a quick announcement. I've gotten a lot of questions about this so far. I do not take attendance, so if you are not able to come to class, for whatever reason, you do not need to tell me because I don't take attendance and I don't pick up anything. So if you miss class, there will be no consequences unless you don't watch the recording. If you don't watch the recording, you won't be prepared for the exam. However, if you miss and watch the recording, you will be completely fine. So if you are not able to make it to class for some reason, that is totally fine. I understand y'all. Most of y'all are juniors and seniors, fifth years. Life gets hard at this point, so please do not worry about it. I know COVID's a big thing as well, so if you're not able to make it, I will always have a recording posted that you can watch. That will be exactly what we do during class. So I'm going to go ahead and hop on into this. I know some of y'all might be watching that already had this in person and are going to finish that last question that we didn't get to in class. So feel free to skip on forward. If you did not come in person, welcome to the beginning. I'm about to write on my iPad with an actual pen. That wouldn't be good. Where's my iPad pen? All right, so again, this is discussion number 2. And before we hop on in, I wanted to go over just some conversions and some units that will help clarify what we're going over today. So we're going to begin with some units. So if you remember back in chemistry, we heavily focused on solving for molarity. And molarity, if you remember, was always kind of denoted by moles. It was kind of showing us moles over liters. So this is what we would see when we were in chemistry. However, now we're in physiology. And in physiology, we're focused on osmolarity because osmolarity is going to tell us the concentration of the body instead of a particular molecule. So osmolarity is very similar. It is osmoles over liters. Osmoles over liters. So we see that is in, oops, that should be capital. It is in osmoles, O-S-N, and sometimes in milliosmoles. And we'll go over how to convert that in a little bit. So in this class, we're always going to be solving for molarity or osmolarity. And to do so, we have to solve for molarity first. So let's go over how we can convert those moles from molarity into osmoles for osmolarity. So in converting moles to osmoles, what we're going to do is we're going to multiply by the dissociation factor. So when we're going from moles to osmoles, what we're going to do is multiply by the dissociation factor. Each molecule has a different dissociation factor, but the main two that we're going to be using in this class, and I highly recommend you knowing, are going to be the dissociation factor for sodium chloride and the dissociation factor for glucose. So the dissociation factor for sodium chloride, is 2. Because whenever you put sodium chloride into water, it will separate or dissociate into 2 different molecules. The dissociation factor for glucose is 1. One other thing I recommend you memorizing for the exam, highly recommending you memorize for the exam, is going to be the molecular weight of these 2 molecules. So the molecular weight for sodium chloride is 58.5 grams per mole, and the molecular weight for glucose is going to be 180 grams per mole. 180 grams per mole. So again, definitely recommend y'all memorizing those for the exam because they will not be given. You find molecular weights on the periodic table and dissociation factors you just have to memorize. So definitely have those in your mind for the exam. One other thing that I wanted to add is that 1,000 grams of water equal to 1 liter of water. 1,000 grams of water is the same thing as 1 liter of water. In this class, we're going to be using primarily liters. So if we ever need to do a conversion, just know that 1,000 grams equals out to 1 liter. All right, so let's go ahead and hop on into the actual worksheet. So here we're going to be having some fun with osmolarity and tonicity. So let's knock this out. What we're going to be doing is looking at different solutions, their osmolarity, so the amount of milliosmoles in them, because we can see right here, Dr. Chang is looking for milliosmoles. So the first thing that I want us to do is understand. So let's understand what these are. So we'll begin with the first one, NS. This stands for normal saline. Normal saline. And what normal saline is 0.9% saline. Saline is sodium chloride. So NaCl. Saline is just some salt added into water. 0.9 grams of salt added into 100 grams of water. However, 100 grams of water is hard to visualize, and again in this class we're going to be using primarily liters. So how we can think of it is 9 grams of sodium chloride and 1,000 grams of water equals 0.9% saline. Out of room there. And if you remember earlier, I told you 1,000 grams is 1 liter of H2O. Nice. So how we got there was we just multiplied that 0.9 times 10 and then added it into our 1 liter of water. So now that we kind of understand what normal saline is, we can now calculate. We can calculate our osmolarity. And to calculate osmolarity, we first have to calculate molarity. So in calculating molarity, what we're going to do is we're going to take that 9 grams of sodium chloride and we're going to divide it by its molecular weight, 58.5 grams per mole. And this is going to give us 0.150 moles. However, this class, we're looking for osmolarity. So what we're going to do is we're going to convert those moles into osmoles. So now we need to solve for osmolarity. Now, how do you solve for osmolarity? You take the moles and you multiply it by the dissociation factor. And for sodium chloride, that is 2. So when we multiply it by its dissociation factor, we're going to get 0.300 osmoles. So now we are in terms of osmolarity. We are now in osmotic terms. However, we're in osmoles, and we see that we're going to be comparing to milliosmoles. So we need to convert those osmoles into milliosmoles, and this is a very simple thing to do. To get to milliosmoles, we just take that 0.300 osmoles, multiply it by 1,000, and we will get 300 milliosmoles. And that is our osmolarity for normal saline. So we're going to take that number, not the one that's highlighted, stop. We're going to take that 300 and we will plug it in to our chart. So we've now solved for the osmolarity of normal saline. So now that we have our osmolarity, we can compare it. We can compare the osmolarity of normal saline to the osmolarity of the body and the tonicity of the body's cells. Then we can look at what's going to happen to our cells based on the tonicity. So what we see is that 300 osmolarity compared to the osmolarity of the body, that's equal. So that means that it's isoosmotic. Whenever we compare it to the tonicity of the body cells, it is also equal, 300 and 300. So that means it's isotonic. And do you happen to remember what an isotonic solution will do to the cell? Absolutely nothing. The cell will remain the same. It will remain unchanged. Nothing will happen. It is equal. It is in equilibrium. Isotonic equilibrium. All right, great. So we have now finished the first row of this chart. So now we're going to hop into the next one, D5 normal saline. So we're going to kind of knock this out in the same method as before. First, we're going to understand what that is. So let's understand what D5 normal saline is. What it is saline plus 5% sugar or glucose. D5 stands for dextrose, and that is a type of sugar or a type of carbohydrate, and every type of sugar has to be converted into glucose to be used by the body. So the only reason we call this D5 normal saline instead of glucose normal saline is because we need to know that 5%. So just as we saw before, we had 0.9% of in sodium chloride in our saline. Now we have 0.5% sugar in our new solution. So what that technically means is 50 grams, because we're going to multiply that by 10, 50 grams of glucose or dextrose and 1,000 grams of water, aka 1 liter of water, will give us D5 solution. All right, great. So now that we understand, we can calculate. And remember, in calculating, we have to solve for the molarity. So we can solve for the osmolarity, and we can convert into milliosmoles. So now we are going to calculate, not calculating. It's late, I've had a long day. All right, so what we're gonna do is we are going to, again, solve for the molarity. So we will take that 50 grams of D5 with glucose. We will divide it by its molecular weight, which again is 180 grams per mole. Definitely want to memorize that. And what that's going to give us is 0.278 moles. 0.278 moles. However, that's in units of molarity. We need to put it in osmotic terms because we are in physiology now. So we will solve for osmolarity. And how do we move from moles to osmoles? We multiply by the dissociation factor. So we multiply by the dissociation factor. And what's the dissociation factor for glucose? 1. So we're going to get the exact same thing here, except now we are in terms of osmoles or osmolarity or osmotic terms. However, we're looking for milliosmoles. So what we're going to do is we are going to convert that even further into milliosmoles. Super easy calculation there. 0.278 times 1,000. That's going to give us 278 milliosmoles. Now, I assume a lot of you would think, okay, let's go fill that into the chart. But remember, we're looking at D5 normal saline. So we need to combine those two now. So we have that D5 plus that normal saline. So what we're going to see is our D5, which I'll label right here. That is D5. So we'll take that 278 and then we will add our normal saline, which we solved for right up here, 300 milliosmoles. And what we will get is 578 milliosmoles for our D5 normal saline. So that is our D5 normal saline osmolarity. So now we will plug this into our chart because that's what we're asked for. So here we will put 578 milliosmoles. So let's now compare it to the body and the cells. So 578 is very much larger than 300. So this will make it a hyperosmotic solution. So it will be hyperosmotic. And I'm assuming a lot of you would think, okay, so it's also hypertonic. However, another trick one, that is incorrect. That's incorrect, and it's super important to know because when looking at tonicity, we only consider non-penetrating molecules. So we only consider non-penetrating molecules. Glucose is a penetrating molecule. It needs to go in and out of the cell for energy use, so it does penetrate that cell membrane. However, sodium chloride does not. So sodium chloride is non-penetrating. It does not enter into the cell. Penetrating. So what we're going to do is we have to do a very small calculation to finish solving this out. So we're going to take our overall osmolarity and we're going to subtract those penetrating molecules. So that glucose, and again down here we solved the glucose or the D5 as 278. So we're going to take that 278 and subtract it from our total because we're only solving for the non-penetrating molecules. So we subtract the penetrating one. And what we're left with is 300. 300 equals 300. So this is going to be an isotonic solution. Again, isotonic solution, that will have no effect on the cell. One thing I forgot to mention earlier is osmolarity does not show the cell's behavior. Tonicity does. Osmolarity is looking at the total body. Tonicity is looking at the cells. So we can tell the cell behavior by looking at tonicity. We do not see cell behavior when we look at osmolarity. That's why we are only considering the tonicity part of this. All right, great. So we have finished the second row. Let's move on to the third. Luckily, we've already done the calculation here, so we don't need to do any calculation. We already solved for that D5, and all we're going to do is add it to water. So this is D5 water. Down here, we solve for the osmolarity of D5 or glucose. We have that 278. So we will now plug that in. Let's see what color I used on my notes, just so I can consistent. I used orange. So we have that 278. And again, we solved that right here when calculating our D5. We just added it to water so that osmolarity did not change. So when comparing this to the body, it's very close to 300. So we're going to consider this isoosmotic. Dr. Chang will make it very clear on the exam. He will make them equal just as we see here. There will not be like a close thing. So you won't have to worry about, is 268 close? Is 258 close? Does that make it below? No, he's going to make it very, very specific, very noticeable. So 278 osmotic, that makes it isoosmotic. And now we need to look at the tonicity. So we can do another little small calculation here. And what we're going to see is we are going to take that total 278 and we are going to subtract our penetrating molecules, because again, for tonicity, we only look at the penetrating or the non-penetrating molecules. So we're going to subtract the penetrating molecules, which is glucose. Glucose is penetrating. So we subtract the glucose from the glucose and we're left with 0. 0 is considerably less than 300, and that means this will be hypotonic. Hypotonic. Hypotonic, I always think hippo. Hippos are below the water. Hippos also like to take a lot in. And when they take a lot of stuff in, they're going to swell. So whenever we have a hypotonic solution, the cell is going to swell. Hypo, hippo, hippos are below the water. They take a lot of solute, a lot of stuff in, and they will swell. Nice. All right, so now we are on our fourth row. Again, we don't need to do any calculations because we already solved for normal saline. This is looking at half normal saline. So we just take half of our normal saline, which is 150. 150 is considerably less than 300, so this will be hypoosmotic. And then for looking at the tonicity, I could do a calculation out here to the side, even though we don't really need to do a calculation. We have that 150. We subtract our penetrating molecules. However, we don't have any penetrating molecules here. Normal saline is non-penetrating, so we don't subtract anything. So we're left with 150. That's still considerably less than 300, so this will continue to be hypotonic. A hypotonic solution that will cause the cell to swell. Alrighty, so now we're on to our last one. What color did I use here? I used pink. So D5 half normal saline, we can do a really small, simple calculation right out here. So we have that D5, which is 278. We will add that half normal saline that we saw before here, 150, and that is going to give us 428. So our osmolarity is 428 milliosmoles. This is considerably larger than 300 when looking at the osmolarity, so it will be hyperosmotic. Now we'll do one more little calculation for our tonicity here. We take that total, 428, we subtract the penetrating molecules, so the D5 part of it, because D5, glucose is penetrating, it goes in and out of the cell. So we're going to subtract that 278, and what we are left with is 150, and 150 is considerably less than 300. So again, this will be hypotonic, and that will cause the cell to swell. Now, if we had a hypertonic solution, it would cause the cell to, it would cause the cell to shrink. And I always think of that because if this were our cell, hypo, O, swell, hyper, you can think of an E, it looks real shrunken. Cool, alrighty. So we have now finished the fun with osmolarity and tonicity. So now we'll move into our actual problems, which are much more applicatory, much more real life application. So we're looking at a patient now. So before we begin to do the calculations down here, I'm going to go over these terms just so you can have some more clarity in your head as we go through this. So deuterium oxide is looking at total body water. Deuterium oxide denotes or shows our total body water. It's normally abbreviated as D2O. So deuterium oxide, total body water. Inulin is looking at the total volume of ECF. So we're looking at the volume of our extracellular fluid. This is normally going to be about 1/3 of the DTO, of the deuterium oxide. Evans blue is looking at our plasma volume, so the volume of plasma. And it's going to be about 25% or 1/4 of the inulin, of the total volume of our ECF. Now, in our calculations today, we're not going to really use that, but it is good to know. Dr. Chang did mention it when he was teaching us this material and kind of paused after. So I definitely recommend possibly kind of knowing that. It can also be helpful when checking your answers. So let's go ahead and take this information and plug it into number 1. So number 1, we're first going to look at the total volume, the total body volume, and we have that up above, 40 liters. Our extracellular volume is 13 liters. And to solve for our intracellular fluid volume, what we're going to do is we're going to take that 40 liters and we're going to subtract the extracellular fluid volume, and we will be left with 27 liters. Plasma, we don't need to worry about that. We are focusing on the cell, not outside of the cell. So do not worry about plasma. Dr. Chang did not go over that with us. He said it's not important. Alrighty, so we have filled in our volumes. We can also fill in our or our osmolarity, which is down here. So our osmolarity is given right here. We have 285. And one thing that we can read in the question and see is that our body's in equilibrium. So our osmolarity will be equal across because our body is in equilibrium. So 285 across. So we've now solved for two variables in each of the columns, which means we can manipulate that initial equation. I don't think I drew it out for y'all, so I'll draw it out in just a second, to solve for our solute. So whenever we are looking at osmolarity, I told you right up here that it is equal to osmoles over liters. Another way we can think of this is concentration, because osmolarity is telling us concentration of water. Osmoles is telling us our solute concentration, and liters is telling us the volume. So this technically equals C equals S over V. Concentration, osmolarity equals solute, osmoles over volume, liters. So with that equation, we can manipulate it and solve for our solute. So we'll take that C equals S over V, solute over volume, and we'll manipulate it using the crisscross method. And what we'll get is S equals concentration times volume. So now all we need to do is some really simple math. So we can first start with the total body. Color did I use over here? We will take our solute equals our concentration, which is 285. And one thing that we're going to do first is, before we do that, we're going to convert that 285 into osmoles, because we can see we're in units of osmoles when we're solving for our solute. So all we have to do to convert milliosmoles to osmoles is divide it by 1,000. So we divide it by 1,000 and we get 0.285 milliosmoles. So up here, this should be 0.285, because we're, again, in terms of osmoles when looking at the solute concentration. So we have 0.285 times the volume, which right here is 40 liters. And once we solve that out, we are going to get 11.4 osmoles, OSM. So we can put that into our chart. And we're going to do the exact same thing for the next one. We'll use that S equals concentration, 0.285 times volume, which here is going to be 13. And when we calculate that out, we're going to get 3.705 osmoles. We put that in our chart as well. And then for the last one, we'll quickly solve that out. Solute equals concentration times volume. When we solve that out, we get 7.695 osmoles. 7.695 osmoles. All right, so we have now completed number 1. Yay. So let's move on to number 2. So number 2, our patient has now ingested 1 liter of water. So they've ingested 1 liter of water. Water has no solute in it, so we're not going to see any changes in our solute concentration, but we will see a change in our total volume. This change is really easy to solve for. All we're going to do is take our original 40 liters and add that 1 liter of water we just consumed. So we'll have 41 liters of total body water. Now we cannot carry that out to the extracellular and intracellular fluid because we don't know the exact amount of that 1 liter that will enter into those. So we cannot trust to carry those initial values down. So we're going to have to solve for that. And how we're going to do so is using our first column. So again, solute does not change. Our concentration of solute does not change. If you're wondering why, with solute, You can think of solute as being example like table salt, sodium chloride. So this is just regular water. There's no salt in it. So therefore, our solute concentration is not going to change. We did not add any sodium chloride to the body. So what we're going to do here is just carry down those values that we solved for above. So we're going to carry down that 11.4, that 3.705, 3.705, and that's 7.695. So now we have two variables in our first column, which means we can solve for our last column. Once we solve for this, our body's in equilibrium, so we can carry it across. We'll then have two more variables to solve for our last blanks. So let's hop into it. So here we're solving for concentration, so we don't need to manipulate our equation. That's C equals S over V, that's solute over volume. We can simply just plug in what we've got. So what we're gonna do is we're going to take that C, what color did I do that in? We're gonna take concentration equals solute 11.4 divided by volume 41. And when we solve this out, what we're gonna get is 0.278 osmoles. So we're gonna wanna convert that into milliosmoles because that's what he's asking for right here. So we'll multiply it by 1,000 to get 278 milliosmoles. So this will be 278. Again, our body's in equilibrium, so we will carry this out across. And now we can solve for our last two variables. So we're going to have to kind of manipulate that C equals S over V to solve for volume. And what we do there, we will have volume equals solute over concentration. So B equals S over C. So now we're just going to do that really simple math. What we're going to do is just solve for the volume. So volume of our extracellular fluid will be solute 3.705, solute concentration over osmolarity, which is 278. When we solve for this, we're going to get a decimal because it's in osmoles. So we'll multiply it by 1,000 to get 13.3 liters. So our extracellular fluid is 13.3 liters. We can now solve for the intracellular fluid. So what we'll do here is the exact same thing. We'll have our volume equals solute over concentration. So we'll have the 7.695 divided by the concentration, 278. We'll multiply that by 1,000 to put it into milliosmoles. And what we're going to get here is 27.7 liters. So we'll plug that in. And we have now finished number 2. Yay! All right, so that's what happens when our patient ingests 1 liter of water. We have a slight change in the extracellular fluid, a little bit bigger change in that intracellular fluid, and then a total change in the total body water. All right, nice. Okay, so moving on to number 3. So now our patient is going to ingest 0.18 moles of sodium chloride. Sodium chloride is also known as table salt. They did not consume salt water. We do not see liters anywhere there. So they did not consume any fluid. They just consumed plain old salt. So what we need to do to solve this one is convert those moles into osmoles so we can make changes to our solute concentrations. So we will now have changes in our solute concentration because we consumed some solute, we consumed some salt. So to convert moles into osmoles, does anyone remember what we do? Oops, that is my thin color. What do we do when we're converting moles to osmoles? We multiply by the dissociation factor. And the dissociation factor for sodium chloride is 2. DF for sodium chloride is 2. So once we do that, what we're going to get is 0.36 osmoles. So we took our moles and converted it into osmoles. We converted molarity into osmolarity. So now that we have solved for our osmoles, we can add it to our solute concentrations. So we're going to take those original values from above, the 11.4 and 3.705, and add that 0.36 osmoles. So for this, we will take that original 11.4, add that 0.36 that we just ingested, and what we will get is 11.76 osmoles. We're going to do the same thing for our extracellular fluid. So we'll take that 3.705. Oops. We'll take that 3.705, add those osmoles that we just consumed, 0.36, and we will be left with 4.065. However, we are not going to change our intracellular fluid because if you remember from up here, sodium chloride is non-penetrating. So it's not going to penetrate the cell, therefore it's not going to enter that intracellular fluid. So we will have our original 7.695. Awesome. So we have now carried out our solute. Again, our patient didn't consume any water, any liters of anything. So we're just going to carry down all of those liters, all of those initial liters from our very first calculation. So we'll have the 40 liters. And since we did consume some solute, we'll leave that extracellular fluid and intracellular fluid alone because the solute might have affected those a little bit. So we'll carry down that total body volume. And we now have two variables in our first column, which means we can solve for that third one, carry it across and solve for those last two. So again, very simple. We just take that C equals solute over volume, concentration equals solute over volume. And we are going to get, we will get C equals solute 11.76 divided by our volume 40. And then we'll multiply it by 1000 to put it into milliosmoles. And that will give us 294 milliosmoles. So 294. Our body's in equilibrium, so we can carry that across. And now we have two variables in each column, so we can solve for those last two. So again, we're going to be solving in terms of volume now. So volume, when we manipulate that equation, is equal to solute over concentration. Solute over concentration. So just our very simple math here again, we're going to take that volume equals solute of our extracellular fluid, solute concentration, which is 4.065. We're going to divide it by the concentration, which is 294, multiply it by 1000 to get it into liters of water, or sorry, liters. And what we're going to get is 13.8 liters. Taking it from grams to liters, so 13.8 liters. We do the exact same thing for that next one. So volume equals solute 7.695 divided by the concentration, the molarity or osmolarity, and multiply it by 1000 to put it into liters. And what we will get there is 26.2 liters. 26.2. Nice. And again, we've now solved number 3. Woohoo! All right, so moving on to number 4, we are now looking at our patient receiving an infusion of 2 liters of sodium chloride, 0.9% sodium chloride solution. What do we know 0.9% sodium chloride solution as? normal saline. Normal saline. Again, normal saline is non-penetrating. It does not penetrate the cell. So we'll first knock out the volume, the total volume, because that's a really easy one. Take that original 40 liters and we add the 2 liters we just consumed to get 42 liters. And what we see is that we now need to calculate our osmoles to change up our solute because they consumed sodium chloride. The solute concentration is going to change. So again, we need to convert that from grams to moles into osmoles. So we have that 0.9%, which means 0.9 grams in 100 grams of water, which is 9 grams in 1,000 grams of water, or 1 liter of water. And we see that we have 2 liters of water. So we're going to take that 9 grams of NaCl and multiply it by 2, which actually, let me do it like this so I don't confuse y'all with the dissociation factor. We'll take that 0.9%, multiply it by 2 to get 0.18%, 18.18% of NaCl. We now need to convert that into moles. So what we're going to do is we will take the 18 grams of sodium chloride divided by its molecular weight of 58.5 grams per mole. And when we solve that, we're going to want to multiply it by 1,000. Or no, we don't want to multiply it by 1,000 because we want to keep it in terms of osmoles. So what we're going to get when we solve that out is 0.615 osmoles. So we can now solve our osmoles by just adding it to those original amounts. So what we're going to do for this one is take that original 11.4 and add that 0.615. That's going to give us 12.016. So this is going to give us 12.016. We'll do the same for the extracellular fluid solute concentration. So we'll take that original, what was our original again, for 3.705, add that 0.615 of sodium chloride that we just received through an IV, and what we will get there is 4.321, lucky number, 4.321. And again, sodium chloride is non-penetrating, so we are not going to enter the cell, therefore the intracellular fluid will not change, and we will be left with that original 7.695. Nice. Okay, so we have now solved for 2 variables in one column, so we can calculate here, carry it across, and solve for those last 2. So we'll use that C equals solute over volume. So C is going to equal 12.016 over volume, which is 42. We'll multiply that by 1,000 to put it into milliosmoles. So what we're going to get is, sorry, don't have my math done for that and don't have a calculator handy on me. What we are going to get is 286 milliosmoles, MOSM, 286. Our body's in equilibrium, so we can carry it out, 286, 286. We now have 2 variables in these last 2 columns, which means we can solve for that blank. So we'll take that equation, C equals SV, manipulate it into volume equals, I can never remember, volume equals solute over concentration. So we will have volume equals, for our extracellular fluid solute, 4.321 divided by concentration, 286. We're going to multiply it by 1,000 to put it into liters instead of grams, and that will give us 15.1. 15.1 liters. 15.1. For the intracellular fluid, we will do that exact same thing. So we'll take the volume and we will take that 7.695 divided by the concentration, 286, multiply it by 1,000 to take those grams into liters. And what we're going to get there is 26.9 liters. So this will be 26.9 liters. And just a quick trick, if you ever want to check yourself, you can add the intracellular and extracellular fluid and it should equal out to the total. So if we take that 26.9 and add that 15.1, we will get 42 liters. That's a way that you can check yourself. Awesome. So we have completed number 4. Woohoo. So last one. Here we are looking at a patient who will ingest 1 liter of water that contains 0.3 moles of urea. So what we're going to do is we are first going to add our liter of water that we consume to our total body of water. So we will have 41. And the way we did that was take that original 40 and add that 1 liter of water we just consumed. And then since we're looking at 1 liter of water and 0.3 moles of urea, we're gonna first just kind of look at what happens when they consume 1 liter of water. We're going to create a second chart to show what happens when they consume that 0.3 moles of urea and that one. 1, 2, 3. 1, 2. Oops. Oh, that's terrible. All right, so here we have that total ECF, ICF. Here we have volume in liters. Here we have solute in osmoles. And then lastly, we have our osmolarity in milliosmoles. So since we're just kind of looking at that 1 liter of water, we can go back to number 2 and just completely fill that in. So we've already solved for that 1 liter of water, so we can fill all of that information back into here. So we'll have that 41, we'll have that we'll have that 41, we'll have that 13.3, we'll have that 27.7, we'll have that 11.4, 3.705, 7.695, and then 278 for osmolarity. So that's what happens when they consume 1 liter of water. However, that water is containing 0.3 moles of urea, so we're going to need to now add that in. So what we're going to do is we'll carry down that 41 liters, but we cannot trust that extracellular and intracellular fluid. So let's now solve what has happened to the solute concentration. Urea is going to change the concentration of solute in the body. So what we're going to do is take that 0.3 moles of urea and convert those moles into osmoles. How do we convert moles into osmoles? We multiply by the dissociation factor. The dissociation factor for urea is 1. He does not need you to memorize that. I think he will give you that on the exam if he uses an example using urea. So what we're going to get is 0.3 osmoles. We get that 0.3 osmoles, and we are now in terms of osmolarity. So we can add that to our solute concentrations. So here we're going to take that 11.4 from our 1 liter. We will add the 0.3 osmoles, and we will get 11.7 osmoles. 11.7 osmoles. We'll do the exact same thing or sorry, we will not do the exact same thing for the next, or yes, we will. I'm not thinking tonight. So we'll do the same thing for our extracellular fluid. We'll take that 3.705. We will add that 0.3. And what that is going to give us is, sorry, my papers are all flying around. That's going to give us 3.791. So this is going to be 3.791 when we add that 0.3. Hang on. All right, y'all, I'm sorry, I made a mistake. So we can trust the extracellular fluid and intracellular volumes because we only consume that 1 liter, so we can carry those down as well. But we cannot change the extracellular solute volume just yet. So what we're gonna do is we will now solve for the osmolarity here. So we will take that C equals concentration equals solute over volume. We'll have C equals solute 11.7 divided by 41. That is going to give us a decimal, so we're going to multiply it by 1,000 to put it into milliosmoles, which is going to give us 285 milliosmoles. So we've got 285, we'll carry it across, and now we can solve for those last 2 blanks. So now we're going to be solving for solute. We have not solved for solute yet, so we're going to manipulate that C equals SV. Oh yeah, we have solved for solute. We'll use that crisscross method with solute equals concentration times volume to solve for those last 2. So we will have S equals concentration, which is 285 times volume, which is 13.3. That is going to give us, where did my math go? That's going to give us 3.791 osmoles. So 3.791 osmoles. And we'll do the exact same thing for the intracellular fluid. Solute equals concentration, 285 times our volume, which is 27.2. And that is going to give us 7.895 osmoles. 7.895 osmoles. Whew, I've taught that 3 times today. This made it 4. I'm going to have no voice tomorrow, but we have now finished discussion number 2. I hope y'all enjoyed that. And if you have any questions, definitely feel free to email me or stay after class next week and we can go over it. But that's all I have for y'all. So I will see you next week. Peace out, everyone.